Hey everybody, it's Ripley again. We're moving on to chapter 3 today, and we're going to talk about measures of center and measures of spread. I'm going to show you some mathematical formulas and some mathematical concepts, and these really are the brick and mortar of statistical analysis. Think of these as the properties of real numbers, or the trigonometric identities, the things that we're going to use over and over and over again. We're going to talk about them ad nauseum throughout this semester. Excuse me, I'm going to get a drink of water. I've generated a small list of numbers here. This is a data set conveniently sorted for our use from smallest to largest. Let's just say for giggles, that I went around to 10 schools in a specific school district and I asked them what their annual budget was in hundreds of thousands. So this would be 4,500,000, which means that it'd be $450,000, $500,000, et cetera, et cetera. This would be 2,900,000, 3,500,000, etc. And it looks like our most expensive school has a budget of $4 million a year. Okay, and I just went around to these schools. Now we got to be careful. If this represents all of the schools in the district, let's say that there are 10 schools in the district, let's call them high schools, then this would be the population for that district. However, it would be a sample for the state or for the United States, et cetera, et cetera. So you got to kind of get this feel for how squishy stats is. Remember, statistics, there are lies, there are damn lies, and then there are statistics. You can write these things sometimes to say what you want them to say. I'm going to assume that this is a sample for now, but I'll make the argument back and forth in terms of whether it's a sample or a population, okay? Because that's really going to matter down the road. All right, let's go ahead and talk about what the measures of center are that we're going to discuss today. The measures of center are the mean, which I'm sure you guys know what it is. It's also referred to as the arithmetic mean. Arithmetic, they're the same thing, mean. Or you'll sometimes hear this referred to as the average. Average, sorry about that. A little extra there. There's also the median. We'll discuss all of these, so don't panic if you don't know them. And we'll talk about the mode. Those are the main measures of center. There's also something called a mid-range, which we'll talk about. That's kind of the average of the highest and the lowest values. So let's go ahead and get started with the mean. I'm going to give you some formulas that are going to make you look real smart mathematically. And we're going to actually do it with this. I'll show you guys tomorrow how to do this on your calculator, how to input it, so you can play with it so that the calculator and or the computer does the heavy lifting for you. Much of everything that we're going to do in this class can be done on either the calculator or the computer. I want to go through the steps with you so that you see how it's done if you had to do it by hand. Plus, I'm evil, and this is the way that we had to do things by hand back when we had to write stuff out by hand. I'm ashamed to say that when I took probability and statistics in high school and college that we had to do much of this by hand. Yes, I'm that old. Okay, so let's go ahead and talk about the mean. First thing we need is the notation. The mean for a sample, if we're talking about a sample here, the mean for a sample is referred to as X bar. If we're talking about a population, it's mu, okay? And this is referred to not as moo like a cow, but mu, and I just think of it like that, okay? Either way, if I'm looking at a sample or if I'm looking at a population, this is equal to the sum of the data values divided by the number in the set, okay? Now, careful. This little n represents a sample. This is a sample size. So you'll sometimes see this written out as the sum of x divided by big N, which is, in this guy, we're talking about the population. You see that how the notation can get a little squishy. So this is actually mu here, assuming that these represent all of the schools in our population. Okay? All right, so what I would do is, if I had to do this by hand, I would simply add 4.5. I'm going to assume that this is a sample initially. I would go 4.5 plus 5 plus ... plus 40, and I would divide by, I think I told you guys that there's a total of 10, and you end up with 19.5. All right, which represents, we know that this represents what, $1.95 million. That's the average. All right, Nothing to it. Excuse me. We've done it 1,000 times. Now, what if our information is in a frequency distribution? Remember how we had those frequencies? Bear with me, you guys, while I find a little piece of information here real quick. What if our information is in a frequency distribution? Sorry, guys, this takes a little bit. Well, it's actually not a whole lot more different. See, that didn't make any sense. The problem is, let's say that our information looked like this, okay? And all that we had was the midpoints and the frequencies, okay? I don't have the actual data. Remember, this data was spawned from this data over here. But let's say that I didn't have this data sitting in front of my head. All that I had was, let's say, this frequency distribution right here, or this in absence of the data. And I have to find a mean. Well, actually what we do is we apply the idea of mean twice. And I'll show you what I mean when I say that. Remember how these midpoints were generated by taking the middle values of these classes. Okay? Now, if all I'm presented is this piece right here, then I have no idea where the data lies around 118.5. I don't know if all of it is 118, 119, 118, 119, 118, 119, or if it's the spread of data like we had here between 113.5 and 123.5. All I have is this. So it's actually pretty simple to find the mean. All I do is I take X bar, I assume that all of these frequencies, and I know that this smells like a pretty big assumption, but statistically it works out really, really well. Instead of worrying about, oh goodness, Ripley, where did the values come from? I don't know where they live. I don't care. I simply assume that they are all 118.5. So in other words, these two data values are going to be 118.5. These three data values are all going to be 128.5. These five, all 138.5, et cetera, et cetera. So what it does is it makes our lives a lot easier. We just take the sum of the midpoints times the frequency and then divide them by n. So in this case, what you'd want to do if you had a frequency distribution like this, you're going to take the product. That's why these things are so useful. You're going to take the product of all of these, and then you add them up and you divide them by n. Okay? Nothing to it. Because think about it. What it would be is if we did, again, we're in absence of this. If we wanted to list our data per the frequency distribution, it would be 118.5, comma, 118.5, comma, 128.5, and this would be 3 times, so 128.5, and then another 128.5, and then et cetera, until we picked up all 28 of our data values. That's really what this says. It's the sum of this times this. This would, which would be what, 137 or 237? So this would be 237 if I did, I can't do that in my head quickly. So 3 times 128.5, enter, that's going to give me 385. 385.5. 5 times 138.5 is 692.5. Check my mathematics. I have a tendency to do crazy things. 8 times 148.5, and that equals 1188. Whoops, 1188. And then 6 times 158.5 is going to be 951. And then 4 times 168.5, 168.5 is going to equal 674. And I'm running out of room here at the bottom. So when I add all these bad boys up, I get 41. Sorry about this, it's down here in the margin, but that's okay. 4128. So my mean is 4128, which was just the sum of all those, divided by 28. And this ends up being, I'm a handy dandy calculator, 147.42. Now, look at where that puts me. That puts me somewhere square in here, which is where it should be, right? I mean, we know by now by looking at distributions, if I look at my histogram, let's see if my histogram's over here, that puts me right in here somewhere, which you would expect your mean or your measure of center to be. All right, now I'm going to scroll back over here, and as we do that, I'm going to talk. The measure of center is supposed to be representative of the most data values. In other words, it grabs all of the data values at once. Now, or no, excuse me, not all at once. It grabs the most that you can grab at a time. All right, now it may not be representative of all. In fact, it can't be representative of all unless all of the data values were the same. In other words, this 19.5 million for, or, yeah, 1.95 million for this data set, it gets pretty close. I mean, it represents in here this little chunk right here. Now, there's an argument that can be made. I mean, let's look really, really closely here. Okay, it's really closest to these two data values. It's way away from this. It's like 1.2 million away from this. It's almost a million away from this. However, we sort of have this Faustian deal with the devil that says, okay, we understand that it's not going to be perfect, but we're going to let it be the center of the data so that we're reducing the differences between the data value and the mean. We're putting it in a place where we hope that it's the most representative of all the data. Like on the histogram that we just talked about, that was representative of a lot of the data. When you have individual data points like this, it gets a little crazy, especially when you've got this great spread of data. I mean, look at this. We start at 450,000. We go all the way up to 4 million. It's going to be really hard to find a measure of center that is representative of the majority of this data, unless all of these middle numbers right here were clustered around 1.95 or 19.5. Okay, now I want to show you something that happens here that's kind of crazy.